Well, here are the problems on chapter 9, statics. I'm going to quickly go over these problems. Some of them are easy while others are a little bit tougher. Okay. So this entire chapter is built on two conditions: that the net force must be equal to 0 and the net torque must also be equal to 0. Those are the two conditions in this chapter. The first problem talks about tightening a bolt using a wrench, and you have the force and the distance. So to find the torque, all you have to do is multiply the force with the perpendicular distance. So you get that as 23.1 Newton meter. So the diagram makes it very clear that you apply the force along this line, and the force is 165 newtons. But what's important is to notice that the distance that you take is perpendicular to the line of action of the force. So this is the line of action of the force, and the distance that you multiply with must be the perpendicular distance from the pivot to the line of action of the force. Now question 2 is a simple one. Two children playing on a seesaw, and the pivot point is at the center. The children are separated by a distance of 3 meters. At what distance from the pivot point is the small child sitting in order to maintain the balance? The distance that is given is actually the distance between the two children. But we need the distance from the pivot. So what we do is, if that is 3 meters, and that's 20 kilogram, that is 30 kilogram, we will assume this distance of the smaller child from the pivot to be x. So we take this distance as x. Therefore, this distance is 3 minus x. Right? So because the total distance is 3, this is x. Therefore, what remains is 3 minus x. And now you know that the 30 kilogram is creating the clockwise torque, and the 20 is creating the counterclockwise torque. So, and their torques must be equal and opposite. So 20 times x is equal to 30 times 3 minus x. When you distribute and do the calculations, you get x as 1.8 meter. So the smaller child is seated 1.8 meter from the pivot, which means the bigger child is seated 1.2 meter away. Now in the third question, you have a 17 meter high and 11 meter long wall. You can't see the 11 meters here, under construction, and it's held up by a bracing. The wall is in stable equilibrium with the bracing but can pivot at its base. That tells us that the pivot is right here at the base, right? Calculate the force exerted by each of the 10 braces. There are 10 braces holding it. If a strong wind exerts a horizontal force of 650 newtons on each square meter of the wall, assume that the net force from the wind acts at a height halfway up the wall. So it's shown in the diagram. Halfway up the wall is where you're assuming the force due to the wind to be acting. Also assume that all braces exert equal forces parallel to their lengths. Neglect the thickness of the wall. Take a close look at the diagram. You see all the forces shown. That's the force due to the wind. You have the weight of the wall itself. You have the normal reaction. And then you have the braces here exerting a force, as you're going to see now. So that is the pivot, of course, that's the pivot, and the force of the wind is creating the clockwise torque, and the distance is half the height of the wall, so the torque would be force of the wind times 8.5, because 8.5 is half of 17. Now the counterclockwise. The counterclockwise torque is set up by the forces in the braces. As you can see, the forces in the braces there, because these two do not have any torque, because it's at zero distance from the pivot. Alright, so we call that FB, and so the counterclockwise torque is R times B. R is the distance times B, FB times 10. 10 because there are 10 braces. And the distance is 8.5 sine 35, as I'm trying to explain in this diagram. Because as you can see, this is 8.5, that's 8.5. You have the angle here as 35 degrees. So this distance, which is R, as you can see in this little triangle here, that's the right angle. This is going to be the opposite side. That's why it's 8.5 sine 35. So when you work that out, you get the answer. But to calculate that, first you have to find the force due to the wind. And that's done by calculating the area. Because what's given in the problem is that the force is 650 newtons on each square meter. So you find the total area, which is 17 times 11. Multiplied with 650, you get 121,550. And then put that into the equation here, and you calculate it to be 2.12 times 10 to the 4 newtons. In the third question, which I will run, I'm letting you see the whole solution because the figure didn't come up in the beginning. You have the drawbridge supported by its hinges here, and the cables are slack, which means there is no tension in the cables, no tension here. And the forces that are acting are the weight of the bridge through its center of gravity, the normal reaction at the other shore, the force here at the hinges, and this angle is almost 90 degrees. So we will consider that this is like 90 degrees to make it easy. So you don't have to break this into two. Now the first condition is that the total up force must be equal to the total down force, and the total up force is F plus N. They must be equal to the weight, which is what's written here. And the second condition is that the torque, the clockwise torque, must be equal to the counterclockwise torque. And when you calculate the torques about this point, that's what the arrow shows. When you calculate it about this point, and the reason why you have to do that is because you're asked to find F. If you calculate the torque here, F will have no torque and it will be taken out of the equation. So we're calculating the torque here. You can see that this is the clockwise torque, which would be F times this whole distance, which is 9 meters. And the counterclockwise torque is the weight, which is here times 7.5. So you have the counterclockwise this way, which is the weight times 7.5. So when you calculate that, because you know the mass of the bridge is 2500, so you know the weight is 2500 times 9.8. Then when you plug it in, you get 20,417 newtons. And the direction is, of course, straight up, which I've written here. It's acting straight up. And then from the first condition, going back to the first condition, you see that you can calculate the normal reaction. That's part B. So just plug it into that and you get it as 4,083 newtons. Since you need the ratio, you divide the normal reaction by the weight. And you get about 1/6 of the weight of the bridge. We're skipping over question 5 because you don't really need that. In this question, a fish has been hooked and is pulling on the line as shown in the figure. The pole makes an angle of 25 degrees, which you can see here with the horizontal. And the distance between the point where the line is attached to the pole and the angler's hand, this distance is 1.95 meter. And the fish pulls on the line such that the tension in the string is 162 newtons. So you see the tension in the string shown here. So 162 newton at an angle of 35 degrees below the horizontal. So you see that here. You can barely see the tension shown. It's right here and it's at an angle of 35 degrees below the horizontal. You're asked to find the magnitude of the torque exerted by the fish about an axis perpendicular to the page and passing through the angler's hand. So you have to calculate the torque here. And the fish is pulling this way. You see that? Which means you have to resolve this into two, the perpendicular and the parallel. Now the reason why we have to do that is to calculate torque, you need the perpendicular force with the distance. Again, the perpendicular force multiplied by the distance gives the torque. So the first thing you do is you break the tension into two. And since that angle is 30 degrees, you see that this is T cosine 30. So you multiply that with the length, you will get the torque. Tension is specified as 162. And the length is 1.95. So you get it as 274 Newton meter. In this question, two muscles in the back of the leg pull on the tendon as shown in the figure. What total force do they exert? Fairly simple because the diagram makes it clear. You have the forces acting symmetrically on both sides, 200 Newton each, and you have the 20-degree angle, and you're asked to find the total force. Now what you got to do is resolve this into its vertical component and its horizontal. Do the same with this. You will have the horizontals cancel out because they are opposite, while the vertical components add up. And what would the vertical component be? Wouldn't it be cosine 20? Because you see that is the, when you complete the right angle triangle here, this is the adjacent side. So you would get each vertical component to be f cosine 20. So to get the total, you have twice that. So it's 2 times 200 cosine 20. That is the total force acting on the tendon. Here is a story about the head and all that. You can read that. But remember that basically it's the muscles at the back of the neck that exert a force to keep the head erect. And that is why your head falls forward when you fall asleep in the class. What you've got to do is calculate the force exerted by these muscles using the information in the figure. So you really need the figure. So here is the figure down there. You can see the force acting at the joint, Fj, that's what it is. The center of gravity of this whole system. The head is here, so the weight is acting straight down, vertically down, 50 newtons. And this is the force exerted by the muscles to keep the head straight. Otherwise, it's going to fall forward, as you can see. So, this is the clockwise torque created by the weight of the head. This is the counterclockwise. As simple as that. Therefore, the force by the muscles multiplied by this distance in meters, that's what you see here, should be equal to the weight of the head multiplied by this distance in meters. Put that, calculate, you will get 25 Newton down. So that's what the muscles have to exert. That's the force. Now for the B part, you know that the net force up should be equal to the net force down. So once you get this as 25, this is 50, the total down force is 75. Therefore the force at the joint has also got to be 75. That's why you have the answer here, 75 Newton up. Now again, there's a figure here. Father lifts a child as shown in the figure. What force should the upper leg muscle exert to lift the child at a constant speed? Now constant speed means no acceleration. That means the net force is 0. Okay, that's understood. And again, I have to show you the diagram. So here it is. Now, the labeling is not that clear, excuse me for that, but basically you see the two clockwise torques, the weight of the child and the weight of the leg create the clockwise torques, while the force due to the muscle creates the counterclockwise torque. So that's what you see here. The weight of the leg multiplied by the distance, which is 0.2, plus the weight of the child multiplied by 0.38. You can make out the distances here, 0.38, 0.2. Obviously, these are in centimeters. Should be equal to the counterclockwise, which is FQ times that really small distance there, 2 centimeters, which you see here, 2 centimeters. So when you do that, you get the weight of the leg. Of course, you have the weight of the leg because the masses are given. Just multiply with 9.8. So once you get that, plug it in here. So that's 39.2. This is 98. And when you do the math, you get it as 2.25 times 10 to the 3. I mean, you got to substitute all those numbers in here and calculate. You will get 2,250 newtons to be the force, which is, as you can see, large. So why you get tired when you do this. And the last one, you find the force exerted by the woman as she does a push-up. And the entire thing is based on the diagram again. As you can see, the forces in this case are the two reactions, one at the hand and the other at the feet. Okay, so you have these two should add up to the weight. Alright, and here the pivot is at this point, of course, because that's where she's turning. So when you calculate the torque, you see that this is the clockwise torque, while this is the counterclockwise torque. This one has no effect because it's at 0 distance. Alright, so there you go. At the pivot, you calculate the torque, and clockwise is the weight times the distance, which is 0.9. Counterclockwise is 2F because she has 2 hands, that's why. 2f times 1.5, which is this distance. All right. So when you do that, you will get the answer. It's as simple as that. And in the B part, I've redrawn the diagram to make you understand the distances. You see the clockwise and the counterclockwise. But to understand that, you have to go back to the question and read that. The triceps muscle exerts a force, and the distances are given as 1.75 centimeters and 20 centimeters. That's where I got those. Muscle by the triceps there. Again, when you calculate the torque, you see this is clockwise and this is the counterclockwise. When you put that in and calculate, you get the answer, because you already got F as 147, which is what I've used here. So the force by the triceps is quite large. It's 1680 newtons. And in the C part, work done is force times distance, which is gain in potential energy. Mass times acceleration due to gravity times the distance in meters. You get approximately 118 joules. And the power is work over time. So take that work divided by the time. Now when you divide it by the time, it says she does 25 push-ups in 1 minute. So you calculate the time for one push-up. Now, there should be no confusion here. It's actually to be divided by time, so it would have been 60 divided by 25. But I've reversed it and multiplied, so it's 25 by 60. Right. 25 push-ups in 60 seconds. So actually the time taken for one push-up is 60 divided by 25, which mathematically is multiplying with 25 by 60. I hope that makes sense. All right, and that is, the unit is joule per second, watts. All right, so that is it. I hope you understand this. Make use of this. Thank you.